Hi guys, a very warm welcome to the first lecture of the RL course. We'll be primarily talking about the K-and Bandit problem, but we'll also go through a very basic introduction to reinforcement learning first, then on to our main topic. Then we'll also talk about various action selection methods, and lastly, the introduction of state. So all of this does not need to make sense to you right now, but as we go further in the video, things will get a little bit more clearer. So what is reinforcement learning? Reinforcement learning is just a machine mimicking how humans learn. So since like day one, since we were babies, we have been constantly fed feedback on by our parents, by our surroundings to do desirable and undesirable actions. And through those reinforcements, through those positive and negative reinforcements, we have figured out how to interact with our environment, right? So that's what a machine, that's what reinforcement learning tries to achieve with a machine. So let's just take a very simple example. So Robbie is a very cute robot and he's learning how to walk. And we make a very simple training algorithm for the same. We suggest that if Robbie crashes, we will give him a punishment. And if Robbie comes across a turn and he does not collide, then we'll give him a prize. So this is a very simple algorithm for training a robot how to walk. And let's just get more deeper into the words or the terminology that is used in RL. So action, agent, environment, and something mysterious that we'll study about at the end of the course. So action. So in case of Robbie, there are only four actions possible. Like Robbie can either go forward, right, left, or backwards. Robbie is the agent himself. So think about agent as the entity who's making all of those decisions in real time and getting affected by them at the same time through rewards. And environment is the one which feeds the agent all of these observations and positive or negative reinforcements. But at the same time, its agent is interacting with the environment to get or extract the maximum rewards. This, in fancier terms, is called as the reward hypothesis. And the environment in this case is the maze because that's like one of the most ideal places to train a robot how to learn, how to walk, right? So a cyclic representation. Let's make a cyclic representation of how in iterations, Robbie is learning how to walk. So the first of the cycle is that the agent or the Robbie performs an action on the maze. And the maze in turn feeds Robbie a positive or a negative price. Let's just call it a reward. And reward, let reward be a scalar entity. So it can be positive or negative at the same time. But also, a very important factor that the environment also feeds Robbie with the rewards is an observation. So Robbie is not that stupid. He knows how to make observations and how to not repeat the same mistakes again. So there are like simple observations that Robbie makes that, hey, if I like, let's just imagine that Robbie was at this point here. So if Robbie was at this point, he imagined that, okay, I've come across a wall and the left is free. I took a left and I received a positive reward. Should I do this more often? Should I take the free left always when I come across a wall? That's how Robbie is trying to learn, right? So let's just generalize this whole cycle into a more big boy language. The agent performs an action A on the environment. The environment in turn feeds the agent with a reward R and observation O. Yeah, so on to the next part of the video, which is the K-armed bandit problem. So think about yourself as an octopus and you have K number of arms. Each arm is capable of performing one action. So each for your first arm can perform the action A1, the second A2, and so on. And the kth arm can perform the action AK. With each arm is associated a unique but a constant reward. All right, a unique but a constant reward for each and every action. So if I ask you how many number of tries will it take you to actually find the action which gives you the most reward? So the answer is pretty simple. You'll say, Sagar, this is a stupid question. All I have to do is I have to take each and every action once, see which reward has the highest value, and then the corresponding action will be just taken again and again. This is a very simple answer, but we won't be studying RL if the rewards were constant. In reality, the rewards are random. They are stochastic in nature. So what do I mean by this? If stochasticity means that if A1 is visited thrice, it is possible that at each time it will give a different reward. So if A1 at time step 1 gives reward R1, It might give R1 dash or something different or something higher or lower. It can be random. That is what I mean by a stochastic reward problem. Now, this is very, very important for you to understand that this is how now we start building upon the mathematics that will help us actually create a preference of which actions to pick. Because now that's what our whole goal is, right? To create a preference for which action to pick. We do this by the using different action value methods, which give us an idea on which action would be the best suited to give us the most reward. So we use the help of mathematics to actually create a quantitative estimate. Again, an estimate that will help us realize which action to pick. So which data do we build this preference or do we build this function upon? So the most naive or the best way to do it would be to just average all the number of times a particular action has been taken and just average all the rewards. So it would give us a quantitative idea of the amount of returns that we, on an average, we get from a particular action. This also works, right? So the whole idea behind this would be to add that at estimate, the action value estimate of action A at time step t would be the sum of rewards when A was taken prior to t. So we are building our estimate on the data that was taken prior to that particular time step upon the number of times A was taken prior to t. All right. So that's pretty intuitive and very easy to understand, I think. So for the reward function, so let's just say that there is an action A and the reward at each and every time step when it was visited is given like this. So if when it was visited at time step 1, it was 1, at time step 2, 15, and at time step 7, it was minus 20. So I want you to pause the video and then create the action value estimate function for the action A at different time steps. So the action value estimate for action A would be kind of look something like this. And here is I have created like a dash here because we do not have anything to build on the first time step. We have no information on action A whatsoever. So we can't average out anything that we don't have even visited. So this is the action value estimate. But at the same time, I want you to ask a question. Pause the video and ask yourself a question. Can we create a bias by using higher initial estimates? Like in this case, we can just imagine this initial estimate to be 0. And then can we create a bias by using higher initial estimates? Because I think that when I come across, like for Robbie, if Robbie came across a wall, I would say that there is a higher bias towards taking a left, right, or going backwards than going straight, right? We should create a bias of somewhat given under some context. But what is the problem with this ideology? Let's just figure that out first. Given there are 5 actions, A1, A2, A3, A4, and A5, at time step T, at time step capital T, the action value estimates of each and every action is given. And after being given this data, you are asked which action will you choose. So of course, we are not stupid and we are not blind. So we will be choosing the action 5. Choosing this action will be greedy. We should keep exploring other actions to make sure if other actions provide a better reward than the greedy ones. Does this statement make sense? All right, let's just go back a bit and understand that rewards were random, right? So what if I keep just using this estimate and actually forget the idea that all these 4 actions don't have random rewards and might have a possibility of giving me higher or more beneficial rewards than action 5. Maybe because they are random, all of a sudden A2 decides that, oh my God, my initial estimate is 11, but I gave a reward of 20. Do you get my point? We have to keep exploring actions in a random way to account for the random rewards. We have to fight randomness with randomness. How do we do that? We do this by the epsilon greedy action selection method. This is one of the many methods we use to counter this problem. So we'll study about more methods further on. So what we do is before even looking, we just close our eyes and we do not even look at the initial estimates of the actions. What we do is we take a probability that in epsilon probability, I'm going to choose a random action. All right. In 1 minus epsilon probability, what I'm going to do is I'm going to think about all of these initial estimates or the action value estimates of each and every action and choose the action which has the highest estimate. We are going to exploit our already known information, which we have used to create action value estimates, and take the most greedy action. Epsilon is in the sake of exploration. Choosing a random action, you might be thinking that if I choose a random action, is there a probability that I choose the greedy action itself? Yes, it does. It actually, there might be a possibility that the greedy action is chosen just because the exploration action is random. But at the same time, we do this to balance the ever famous problem of RL, exploration versus exploitation. And there are many more methods which counter this problem, and we'll learn about them in the next section. So we'll be looking at some more ways for action selection. The first is the gradient bandit algorithm. So the gradient bandit algorithm uses the softmax distribution function or the Boltzmann distribution. What it does is it distributes probability to each and every action of being picked, and that probability is directly proportional to the action value estimate. So h of a is actually denotes the action value estimate, and it put it is put to the power of e. But at the same time, we have to realize how does it counter the exploration versus exploitation problem. If you think about it, that even if an action has a small action value estimate or a small action value function, you have to realize that it's still on the table of being picked. It still has a probability of being picked. So if all the actions are still on the table, if none of the actions are being ignored, exploration versus exploitation is being taken care of. But of course, larger preference is given to those which have a higher action value function. The upper confidence bound, this is a formula that is a little confusing and scary to look at first, but let's break this down. So this algorithm dictates that the action that will be picked at time t will be the action for which this expression has the highest value. So this we already know is the action value estimate. We do not need to break that down more. So this is the uncertainty factor in the estimate. The uncertainty factor is increasing with time t, and it has a quite of a sense. It's like quite senseful also, right? Because if the time that I have visited action is increasing, if I visited an action, let's say at time step 1, and I'm revisiting at time step 1000, the uncertainty is of course increasing with the amount of time. So that's what the LNT factor represents. And the N of A action represents the number of times we have visited A. So of course, if I visited A larger number of times, the lesser the uncertainty will be in the estimate of the function. So that is upper confidence bound action selection for you, and such a clever way of actually countering the exploration versus exploitation problem. This is the optimistic initial value. So earlier in the lecture, I asked you, can we create a bias by using higher initial estimates for one particular action? The answer was yes, we can. But what if we create wildly optimistic initial estimates for each and every action and all of them are equal? Which means that if the initial estimate is optimistic, which is optimistic signifies that it is higher than the rewards that it can possibly give. That each and every action, let's say, can give a maximum reward of 10. I'll keep an estimate of 15. So this is an optimistic estimate. So if I provide this to each and every action, what will happen is that after exploration done on all the 5 or all the k number of actions, it will all of them will converge to the true value after multiple iterations. And that's how the exploration versus exploitation action or the exploitation problem is addressed with this algorithm. So some valid questions that we need to ask: that is there a better way to judge which action we should take? Can that way be more dependent on the context or the environment and not just empirical evidence? So till now we have been creating preferences for actions through mathematical functions obtained by the rewards that we have gained till time step t. That's what we have been doing since like last, I don't know, like 20-30 slides. How do we actually create a preference, or how do we create a how do we build more information into our decision? So back to this slide where we talked about some basic terms that are used in RL, action, agent, environment, and the four term that was left for the end of this video, and it's state. So state here in this case is Robbie's position in the maze and his orientation. Why did we need to introduce state into the equation? So the questions we have asked till now is that which action will give us the most reward? And we have based our answer on this question on the information of past rewards and making an estimation on empirical evidence using mathematical functions. But is that all to it? Is that all we can depend on to make a decision on which action we should pick? Thankfully, no. Here's where state comes into play. State is the necessary information about the environment that is observed by the agent to make a decision. So, a very important one liner that I need you to like ripple into your minds is state is introducing context into our RL problem. State is training the agent to actually observe the environment and judge which situation demands for the best action. And that's why state is important. Next up in the lecture would be Markov decision process. And thank you so much for sticking through the end of this video.